local heat or a remote heat. So let's assume that I've just started my application, and let's assume that on this node I've previously written A, and in this other node, another application had written the pair B beta on the cache. So if on this node I try to read the key value A, I will get back alpha, and I will get that through a local heat. But if later on I try to read B, as you can see, B is not necessarily on my cache right now, so this will be resolved through an internal protocol, a very optimized protocol, in order to deliver to the application running on this node the mapping between B and beta, so the key value pair B beta and thus beta to the application running on this node. So in this case, it's still a heat because the value is on the distributed cache, but as you can see, it's a remote heat. If we then later on in an application running on this node and remaining on this state of the cache try to access C, then you see that there is no C, neither locally nor remotely, and in this case then a mishandler will be called on this node, and that mishandler will be able to recover the value somehow. Okay, so we have explained how OpenSplice EDS minimizes the heat time. Let's try to see what we can do about miss rate minimization. So cache misses can be really classified into three classes. There are compulsory cache misses, capacity cache misses, and conflict cache misses, or cache misses due to conflict. So compulsory cache misses are due typically to first access of data. So when you're trying to access a data item which is not in the cache yet. These are also known as cold start misses or first reference misses. Capacity misses are actually due to the fact that you don't have enough memory to store your working set. So if your application needs 100 value, but you only have space for 70, and if you access all those 100 quite quickly, okay, and are really part of your working set, then you're sort of stuck. That means that you don't have enough memory for it. So what you can do? Well, I will show you that actually OpenSplice EDS also alleviates the capacity misses issues. And then the third point is the conflict. So depending on how you actually implement the cache, the software cache, you might have that different key value pair ends up competing for resources even if there is enough space in the memory or available space in the cache memory. So that's a very important aspect because ideally you would like to have a cache implementation that doesn't suffer conflict misses. So OpenSplice EDS, with respect to the miss rate minimization, has really been designed so to really reduce at the minimum the misses due to these three classes. So let's see what we can do about the compulsory misses. So we use the popular prefetching techniques, and we provide you a way of customizing how you can do prefetching in order to minimize, if not eliminate, depending on how you code your application, the compulsory misses. So the basic idea is the following. We try to figure out what is the temporal and spatial correlation of the data that the various applications use, and we already have a protocol that automatically preloads the cache by exploiting the space that is already available or editing data that we can tell you won't use anymore, okay? And again, there are configuration parameters that allow you to tell our middleware when you can consider that some data is old enough that you won't use it anymore, okay? But really allow us to prefetch data and fill in the cache with value that we believe you will use soon enough, so that whenever you need them, you actually find them already locally without experiencing a remote heat, but just having a local heat, which means, few microseconds versus tens of microseconds. So that's very powerful because essentially we make it possible for you to make sure that whenever you need data, data is already there because the middleware has preloaded it. Moreover, we have an API that allows you to customize how the prefetching works. So you can tune the prefetching to the needs of your specific application. So let's take a look at a simple animation that will illustrate how this prefetching works. So I have now the cache that I was showing in the example before when I was going through the concept of local and remote heat. And you see that I still have the A alpha and B beta key value pairs. But I've also done on this node a write, and I've written the association between S and sigma. So you see, in fact, it here. What will happen in this case? So in this case, the middleware, assuming that the prefetching believes it's something you're going to use, will preload this value on all the other cache instances. And look at the color coding. So the green indicates a working set because, well, you have written, so you've been utilizing these, and we had read A before. But this is not working set yet. So these items are simply prefetch items that you might be using soon and that we will manage again as prefetch items. And by the way, you can also configure the amount of cache, of free cache, that we can use for prefetching. Now, if you do now a read of S on this other node, the good news is that you will experience a local hit. So that's very good because, again, we managed to prefetch data and to have you find the data exactly where you need it, when you need it. So that's pretty powerful, and you can understand that can dramatically boost your performance far beyond what current caching technology provides you. Okay, so let's see what we can do with respect to capacity misses. So as I was explaining before, you typically have capacity misses when you don't have enough memory to store your working set. Now, if you don't have enough memory, then, well, you don't have enough memory, so what can we do? In OpenSplice EDS, we can exploit the concept of remote cache hit to ensure that perhaps if you have, some other node in your system that maybe is not embedded and has enough memory, that the working set for your specific embedded node is partially maintained by a few other nodes that are, richer in terms of resources, and so that your working set will be resolved by means of remote hit. So that's still pretty good because we are still having a hit, and in a sense we are circumventing the capacity constraint of a resource-constrained embedded systems and leveraging perhaps the capacity or the resource available on some workstation or higher-end server that is still deployed on the same system. Okay, now the last point that we need to cover in order to understand how we minimize the conflict misses is cache organization. So by default, the OpenSplice cache behaves as a fully associative cache managed by the least recently used replacement policy. So we took this choice because this practically eliminates the conflict misses due to different data items that maps to the same actually slot within a cache. And at the same time, the choice of the least recently used replacement strategy was motivated by the fact that theoretically, using a competitive argument, you can prove that this is an optimal replacement strategy. So by default, that's what you have. This should work. This typically works very well for most applications. But if you have an application that has some specific pattern that is very predictable, and you already know that maybe there is something that that you can do because essentially you can predict exactly what your application will do. Okay, then you can still plug your own custom caching replacement strategy because there is an API for doing that, and for some application that would make sense. But again, the good news is that regardless of whether you use the least recently used under the assumption that you cannot predict the future, or you customize the caching replacement strategy with your own strategy, assuming that you know how to predict exactly your application, in any case, you are getting the best behavior, okay? Because you're just changing the assumption. But if you don't know how to predict the future, then there is nothing that can do better than LRU. And if you can predict the future because you know exactly what your application does, then again, you can do better than LRU, and we allow you to plug your own replacement strategy policy. So that's pretty good.